Please take your seats as we will begin shortly. Good evening, everybody, and welcome to the Monash Uncrewed Aerial Systems Showcase Night. I'd like to start by saying that Monash UAS acknowledges the Bunurong people of the Kulin, traditional custodians of the land on which we gather here today. We pay our respects to the elders, past, present, and emerging. This always was and always will be Aboriginal land. I'm Daimi, and I'll be your MC for tonight. Before we dive in, I'd like to take a moment to thank each and every one of you for being here. From family to friends to sponsors and to faculty, your support really means a lot for the team. So a round of applause for such an amazing turnout. With that being said, please give a warm welcome for the 2025 Monash Uncrewed Aerial Systems Team Lead, Nikhil Pokharel.
Thanks, Taimi. Wow, what an incredible turnout. I think we've actually broken our record here tonight in terms of an MUAS showcase, so that's pretty cool. Thanks, everyone. Over a decade ago, a small group of students gathered together to build a drone that demonstrated the incredible potential of such technology. Since then, our team has grown to over 100 members, and our vision has also evolved. Monash UAS demonstrates the humanitarian potential of drone technology while inspiring the next generation of engineers. The second part of that statement, over 100 extremely dedicated individuals, when facing the challenges associated with running a student team, have persevered, fueled by little more than their own passion. Tonight, you're going to see a culmination of all their hard work, and they're pretty excited to show you. So yes, while we're here to celebrate our achievements and the things that we've created, I think ultimately we're here to celebrate the students and what they're capable of and what they're going to go on to do. Many of you have seen what we have done before, but for some of the newer faces, here's a rundown. Joining me at the helm this year is Thomas Buno, Chief Engineer, Partner in Crime. Partner in crime was a joke for our Vic Police friends here. Aerostructures, led by Ruben and James, is the backbone in the design of our aircraft. They're responsible for designing, creating, and developing our airframes, utilising the latest materials and techniques. From conceptual design through to in-house manufacturing, they ensure our aircraft are optimised for performance and durability. The avionics section is responsible for bringing our aircraft to life, designing and implementing onboard electrical systems vital for the function of our aircraft. At the core of MUAS's search and rescue mission are many of the projects within this section. And as you'll learn tonight, the technologies they are developing have the real potential to advance drones in the humanitarian field. This team is led by Ethan and Emma. Flight operations, led by Nicholas and Saskia, are responsible for turning designs into reality. They handle the final integration of systems, ensuring the aircraft is flight ready. During missions, they manage ground station operations, analyse telemetry and flight data. Our incredible pilots oversee both manual and autonomous missions. They ensure safety and precision in every flight. This year, our lead pilots are Rohan and Hamish. Propulsion, led by Say, is a relatively new section, but despite that, this section will push MUAS further than ever before. By developing custom components, including motors, ESCs, propellers, and more, propulsion aims to outperform the off-the-shelf products that we have always employed, in turn improving our capabilities at competition. With the innovations of this section, our drones will fly further and faster than ever before. And the section that holds us together, operations. From managing relations with partners, running outreach programs, recruitment, and general logistics, this diverse section ensures the smooth functioning of our team, this year led by Darren. Tonight you're going to get to hear them all speak, but please join me in a round of applause for the members leading this team this year.
Throughout the last year, all sections of this team have been working tirelessly to advance the incredible accomplishments of 2023. Please welcome Dilshan, our 2024 team lead, to remind us where we left off.
Hello everyone, hope you're having a wonderful evening so far. I remember just over a year and a half ago, we had just finished our 2023 demonstration of the aircraft Albatross, our search and rescue platform. We had spent the last couple of years developing all the different search and rescue tools in order to ensure that we had a very reliable platform that we could then develop. Leveraging that momentum, we then chose a courageous goal: to take part in the new flying competition, the first international competition our team would ever partake in, while also continuing to develop our search and rescue tools on the Albatross. The team has worked tirelessly, and I know after tonight's presentations, you will all be in awe at how we've taken such a bold claim and turned it into a goal that we are so close to achieving. Before we get into showing you all the new work that we've completed, I'd like to show you guys with a reminder of exactly where we're up to in our incredible mission.
Coming off such successful achievements with the Albatross, the team was well equipped to hit the ground running. Please welcome Saskia Milne, one of the flight operation leads, to explain how we utilized this productive momentum.
Thanks, Daimi. After a very full summer of testing on the Albatross, flight operations began 2024 with a small but dedicated group of only 4 members, who collectively were responsible for all flight day operations, aircraft assembly, and flight analysis. With immense workload on the horizon, last year's section leads commenced a rigorous recruitment round and split flight operations into 2 projects: ground station and aircraft management. Our ground station project have been transforming one of the 2 hard cases we own into a mobile operations station to take to flight days. This provides a much more elegant and functional base of operations on our flight days than our current setup. This station must be capable of running our telemetry and communications software Mission Planner, and in the future, our in-house built software for mission management. It will be imperative to our success in upcoming competitions. Our aircraft management project have been responsible primarily for the maintenance and modification of 2 formerly DJI aircraft, the S800 and the S1000. I say formerly as our modifications at this point are so extensive that to call them by their commercial off-the-shelf names feels insufficient. These 2 drones were very generously donated to us by the Monash drone discovery platform. These drones have now been integrated with our flight controllers and our wiring conventions, and all the avionics projects are configured to be mounted on one of the 2 drones. This has allowed us more flexibility for parallel testing of projects for both aerostructures and avionics, but has especially accelerated progress for avionics projects, as we are now able to test them independently of our more complex, fully integrated platforms like the Albatross. And the next video we have to show you goes into more about our S800 Hydra and our S1000 Kraken.
Over the course of 2024, Flight Operations has modified our 2 existing DJI platforms, the S800 and the S1000, in order to allow avionics to test their projects. These drones have been adapted with Cube Pilot Cube Orange flight controllers, HERE 4 GPS units, and 900 UX RFDs, as well as other additions. The S800 is our 6-rotor multi-rotor, also known as the Hydra. This drone has been typically used for testing the avionics vision projects, as well as helping to train our remote pilots. The S1000 is our 8-rotor multi-rotor, also known as the Kraken. This drone has been used predominantly to test the avionics Lifeline project, but has the capability to test any of the avionics projects. Further changes have been made to some of the structural elements of this drone, such as adding mounts and redesigning the rotor arm clips to better help flight operations do maintenance on the drone more easily. Prior to having these drones, avionics acquired the team's previous drone, the Albatross, for all their testing. Due to the size and complexity of this aircraft, it proved to be inefficient when wanting to test these projects at short notice, as it requires a lot of equipment and personnel just to test a small upgrade to a project.
You would have seen in that clip one of our oldest sponsors, Cube Pilot. As of this year, our collaboration is now 5 years old. Cube Pilot provides us with the industry-leading Australian hardware which brings our aircraft to life, our aircraft's flight control systems. Over the years, their continual investment in our team has only fueled the enthusiasm of our members. An opportunity to work with their incredible products is not one we take for granted. As such, I would like to warmly invite the CEO of Cube Pilot, Philip Rouse, up to the podium to speak to you all now.
G'day. Thank you very much. It's been amazing to sponsor this team for 5 years, to watch them work and to do really cool things like upgrade DJIs to Australian autopilots and get rid of the other stuff that was on there. It's actually interesting when you look at the heritage of the DJI equipment, because the Phantom 3, which many people here might know, had a copy of our original design in the heart of the thing in the first place, so it is only appropriate to send it back to its roots. So, yeah. I was asked to give a speech on the humanitarian needs of the industry, and I want to twist that up a little bit and talk about the fact that the Australian drone industry is the heart of the worldwide drone industry. Every single drone that you see in the news has some heritage in Australia, whether they were designed here, whether they're copies of designs from here or derivatives of that. But most of the software that even runs on them, like the ArduPilot or PX4 software, has Australian engineers at heart. A lot of that has come from challenges like the competitions these guys run at. Back in the days when we had the Australian Outback Challenge, and other competitions like that, it was university teams that pushed the boundaries, that pushed our code to do really cool things. And the motivation for most of the people that I know who got into this industry has always been search and rescue, life-saving. What got me into this industry was drones and firefighting, and that really has been most of our focus. The news these days doesn't paint that picture. So it's really important that we actually do come back and focus on all of those really positive uses of drones, and I really love that this team has put that at the heart of what they do, is search and rescue and positive uses. Some of the applications, we were up here last week with the team talking about what to do with drones in a humanitarian role, and there's things like, delivering defibrillators and just delivering insulin, some of those basic things that by now should actually just be normal. But it's actually still very hard to get that stuff done because we do have a lot of rules and regulations in the industry. So it's good that we can focus on those positives, and I really appreciate the team doing that. The other thing is building up the industry in Australia. Yes, Australia is the centre of the drone industry, but unfortunately, everyone who gets really good in the drone industry goes to America, goes to Europe, somewhere else where they pay well. And there does have to be a certain level of passion to actually do drone work in Australia. Your motivation needs to be Australia and drones, not necessarily becoming the next billionaire. And so I think it is important that people come into this industry with a passion for the industry, because that future that Australia needs in drones is really going to be driven by people who are passionate, join groups like Monash, UAS, and so there are jobs in Australia. It might be as fancy as Silicon Valley, but we provide the brains to Silicon Valley. So you would have seen on the thing, this is our sort of staple autopilot. You see these little orange cubes popping up all over the place, and At the moment, we're putting in an assembly line in Geelong to build our next generation autopilot. They basically do the same thing, and that'll be coming off a production line in Geelong, 100% made in Geelong. So we are bringing our industry back to Australia, in this case Geelong. I know it's a little bit far from here, but it's a lot closer than Taiwan, where we're actually putting these ones together at the moment. So yeah, really appreciate everything this team does. Thank you for having us here, and we look forward to the next 5, 10, 15, 20, whatever years of sponsorship and what you guys do. Thank you.
Thank you, Philip. Your partnership with MUAS has for a long time been a core element of our operations, and I'm sure it will be for years to come. Hello, everyone. My name is Ethan. Emma and I are the avionics leads for MUAS in 2025. Throughout 2024, the avionics section has been highly focused on developing and improving technology for search and rescue applications. Our ultimate goal is to develop systems that have the capability to save a life. Our section requires a diverse range of skills, spanning hardware, software, and mechanical design. Many of our projects involve members from multiple disciplines, which we believe prepares our team for industry, where collaboration across different fields is essential. 2024 saw avionics make significant progress. Our payload deployment system, codenamed Lifeline, had a successful in-air deployment for the first time. We began and are now well along the way to developing a biaxial antenna tracker for improved communication range. And our AI vision team has successfully trained a model to detect not only humans, but also a number of other objects that would be found in a search and rescue scenario.
Of course, these search and rescue focused projects could never have taken off without the support of our other core avionics projects. The Power Distribution Board team, which is responsible for distributing power to all auxiliary systems with a custom circuit board. The Avionics Stack team, whose members work night and day to ensure that all systems are powered and that our aircrafts have robust and efficient wiring harnesses. And last but not least, our mission management team, who allow us to monitor our aircraft during flight testing. As a section, we also shifted our focus towards developing new systems that would integrate across all our existing avionics, enhancing our overall capabilities. One of our new projects, Detect and Avoid, is aimed at creating an object avoidance system to prevent collisions with both static and dynamic obstacles during flight. This system will enable us to fly multiple aircrafts in the same airspace, significantly improving our search and rescue operations. Already, this project has developed a simulation proof of concept of both static and dynamic objects avoidance, which is a technology that is infinitely useful in both competition, but also in real-life air traffic control. Both Ethan and I feel incredibly fortunate to be leading such a talented group of engineers who are as passionate as we are about the humanitarian potential of UAV technology. We would also like to extend our gratitude to Maddie and Kian, our predecessors, for the hard work they put into shaping and developing this section, and for their invaluable advice as we stumbled through our first few months. Without further ado, let's hear from some of our search and rescue projects about their developments in the past year.
In our pursuit of aiding humanitarian rescue, we are excited to present Project Lifeline. Initiated in 2023, Lifeline's purpose is to develop a robust payload deployment system that can deliver a box full of medical supplies from our aircraft to a patient in need on the ground during search and rescue operations. The system is controlled by a Raspberry Pi, programmed to receive specific MAVLink signals from the ground control station and act accordingly. Once it is time, the payload will descend to its targeted location via a tethered freefall. Multiple PI control loops are employed in our braking mechanism in order to ensure a smooth and safe deceleration as the payload approaches the ground. Eventually, the payload will be slowed to a stop a few centimeters off the ground before our final release. Lastly, to fully release the payload from the aircraft, a nichrome wire is heated to burn and cut the cables in a fraction of a second, allowing the payload to fall onto the ground quickly and safely. Lifeline has come a long way since we started, and we are not planning to stop anytime soon. A newer, improved release system is being designed that releases the payload through a mechanical latch before winching the remaining cables back into the aircraft, eliminating cable wastage.
I'm excited to present the Vision Project, a system designed to detect patients and provide highly accurate GPS coordinates using artificial intelligence. This technology has the potential to improve search and rescue missions by enhancing our ability to visually locate key objects, such as patients in distress. Over the past year, we've made significant progress in advancing Vision's AI model, software, and hardware. On the AI side, we've expanded our mission objectives and capabilities. Originally, Vision focused on detecting patients, but now it can recognize key objects crucial for rescue missions, including tents, backpacks, clothing, fire, and more. These additions provide more context and improve situational awareness during rescue efforts.
Software improvements include AI model switching mid-flight, which allows us to optimize detection based on various terrains. We've also begun developing a map generation function capable of creating a Google Earth-style map to help rescue teams locate the patient more effectively. On the hardware side, we've continued improving the gimbal system, which stabilizes the camera and allows precise directional control during flight. We've also refined the mounting and dampening system to improve the quality of our footage. These advancements bring us closer to making Vision a powerful and reliable tool for real-world applications.
Moving forward, we aim to refine these capabilities, enhance integration with rescue operations, and explore night vision functionality.
We reflect on an exciting year for Monash Uncrewed Aerial Systems, or MUAS, as most of you are aware. It's been an absolute privilege to see this incredible team thrive and achieve extraordinarily milestones. This year, we've reached new heights, both literally and figuratively. Tonight, Showcase 2025 is our biggest event yet, with over 200 attendees, including industry professionals, some sponsors, and family members and friends. This event reflects how far we've come. A major highlight of this year was our involvement in the Anzac Airshow, with thousands of attendees, where MUAS was invited to set up a display at the 2024 West Sale Anzac Airshow. Our team had the opportunity to network with industry leaders, further establishing MUAS's presence in the aviation industry and the aerospace industry. As I'm sure you're all aware, we're on a mission to inspire and educate the next generation of engineers. From mentoring students at John Monash Science School to hosting workshops with the likes of Monash Engineering Girls, where we actively encourage young women to consider engineering. We're building a future that's dynamic, inclusive, and full of potential. And if you thought that was impressive, we've also reached over 14,000 people across our Meta platform, which is a 100% increase over last year. Together, we'll continue to soar. Thank you.
It is truly amazing to see how far we have come and how much we have grown as a team. Now I'd like to introduce Tom Buno, our Chief Engineer for 2025, to delve into our goals for the upcoming year.
Hello, and thanks, Daimi. As you've previously heard, the last 12 months have been an incredibly busy time for us, and I'm excited to announce that we'll be hosting another demonstration at the end of this year to showcase the latest versions of our search and rescue projects. Our demonstration will simulate a real search scenario. There is a missing person, possibly with a medical condition, who is known to be within a particular search area. Monash UAS will search for the missing person, and once found, will deliver life-saving supplies, send their GPS coordinates to a rescue team, and monitor them until the rescue team arrives. To demonstrate all our mission projects, we will be using multiple specialized multi-rotor platforms. The mission tasks will be split between two aircraft, one specially outfitted for searching with our vision system on board, and the other will house our lifeline system to deliver the potentially life-saving supplies. This upcoming demonstration is an important milestone for our team, and we're incredibly excited to share these advancements with you. But our ambitions don't stop there. We're also preparing to take our skills and expertise to an international stage where we'll put our aircraft to the test against some of the best teams in the world. This year, our team will be taking on one of the most exciting and demanding drone competitions in the world, the New Flying Competition 2025. Set in Hamburg, Germany, the competition brings together the brightest minds in aviation and robotics to push the boundaries of sustainable flight. The mission is clear: design and build the most efficient electric aircraft while maximizing performance and payload capacity. Each team must outperform a reference aircraft built by the event organizers across a series of rigorous flight tasks. Points are awarded based on performance and efficiency. The competition consists of two main segments: performance and endurance. In the performance flight, our drone will be tested across a range of capabilities, as shown in the diagram behind me. This flight sequence includes a high G maneuver, which in our case will be a vertical loop, as well as a controlled glide and two maximum and minimum speed runs. Now, the endurance flight, while a seemingly simple concept, is one of the biggest challenges of the competition, and as such, carries a significant weight in the scoring. Essentially, we must fly as far as we can using as little energy as possible. And for the first time tonight, I can reveal one key aspect of our competition entry. Our aircraft will be a fixed-wing, conventional takeoff and landing drone. But that's all I can say for now, and more will be revealed throughout the showcase. Thank you.
With the NFC competition guidelines and requirements known, the team embarked on an incredible task of designing and building a brand new aircraft to compete. I don't know about you, but I've certainly noticed a rather large object in the middle of this room that we have yet to see. Well, all your questions will be answered shortly. But before we get to that, we have put together a presentation that details the birth of our New Flying Competition, or NFC aircraft, an aircraft called the Peregrine. From design to reality, here is how to build a drone. First up, please enjoy this short video on the initial conceptual design phase. Here, we began to turn our early ideas and scoring optimizers into something real.
Our mission at NFC 25 is to score higher than the hosting team in these categories, each with their respective weighting factor. After carefully evaluating the constraints, our priorities, and the design complexities of each of these categories, we've chosen some to be our control variables and the rest to be parameters to optimize for. Now, with a few parameters to work with, we began the development of our in-house optimizer, Athena. Athena is able to iteratively tweak the control variables, compute the dependent variables, and calculate the respective score using a method called gradient descent. Gradient descent is a popular optimization algorithm often used for machine learning with multiple variables. In our case, this helps us to determine the best configuration to maximize our score. Now, our team was able to create a CAD model parametrically with Athena's output as we move on to a higher fidelity analysis with ANSYS's Fluent Computational Fluid Dynamics, also known as CFD software. CFD provides a better insight into the prototype generated by Athena, as our design team made subsequent adjustments to the geometry to ensure that the final model has a similar, if not better, performance compared to the Athena model.
Hello everyone, I'm Say and I'm propulsion lead for this year. Propulsion has been hard at work for the past year since its conception. With a strong cohort of now 16 members, we have been diligently researching and developing our various components in the propulsion system. The past year has involved rapid development and growth of both our knowledge and technical skills in areas that have rarely been touched by us before. We have managed to produce and test custom designed propellers and electronic speed controllers and are very close to making our first motor. These are what we have done so far. From here, we plan to optimize our designs and improve our system as a whole by incorporating a constant speed unit into our system. This next section of how to build a drone will showcase our initial CSU and ESC designs and our current development on our motors and how we have been aided by the use of FEA. We will also be showcasing our propellers and how we have validated their performance on our thrust test stand, the cassowary.
Inverters, also known as ESCs, handle the driving and controlling of the main propulsion motors. The Inverters project aims to replace the commercial systems currently used on Peregrine and other UAVs as custom-tailored solutions that integrate the functionality of multiple previously individual systems to deliver greater efficiency, repairability, and value. Although we are a small project that was founded just last year, we've already delivered a proof of concept called Phoenix V0 that has validated our design, manufacturing, and testing processes. We are currently in the testing phase of our next generation system called Phoenix V1, which incorporates a fusion of open source and in-house technologies that give us the edge over the competition. Our innovative modular design allows for fast testing and validation, as well as a unique level of configurability and repairability. And our integration of the advanced FOC algorithm with closed-loop control improves motor efficiency and torque across the entire speed range. All these innovations will yield significant improvements to propulsion efficiency and performance and reliability. And we aim to complete our design validation and have our inverters flying this year.
The CSU, or Constant Speed Unit, permits the changing of a propeller's pitch during flight. While systems like this are plentiful in the full-scale aircraft space, and systems with broadly similar requirements are present in most RC helicopters, the high RPM and considerable pitch range needed to maximize our motor and aircraft's performance necessitated the design of an in-house solution. With the ability to design and manufacture them in-house, we can optimize our propellers for any number of flight conditions, but to optimize a propeller for a range of conditions, it will always be necessary to make compromises as to the propeller's performance. By allowing both the speed and pitch of the propeller to be changed during flight, these compromises can be mitigated.
In addition to widening the performance envelope of the propellers themselves, the CSU allows for some additional bonus functionality, like reversing the thrust and prop feathering, which is intended to give the Peregrine a competitive edge in the maneuvering flight. Combined, these features allow us to maximize our propeller performance in the efficiency component of NFC without having to sacrifice our aircraft's performance at the edges of its flight envelope.
In order to accomplish all of this, an extensive design cycle was undertaken. The result is that the CSU has been carefully optimized so that no space or weight is wasted, key to both the success of the aircraft in competition and to the survival of the CSU during flight.
Now it's time to make some props that get the best performance out of our motors and CSU. Propeller design starts right at the basics, determining a desired performance of the propeller at a specific operating point. Once chosen, the necessary parameters are loaded into our custom PropCalc software. Written in-house by MUAS members, the program takes an initial shape and a desired performance. Within a few minutes, returns a propeller geometry optimized for our desired thrust and torque.
Once we have our geometric data, it's onto the CAD phase. Here, we take the data produced by PropCalc and use it to create a 3D model of our propeller and a mold for it in Creo. The CAD for the mold is then converted into a CNC program and it's onto manufacturing. We load our program into the CNC machines and let them carve out the molds. Where rapid iteration is needed, machinable wax is used for fast and reusable molds, and where an established and mass-produced prop is needed, aluminium is a UAS staple.
After the mold is created, it's over to the composites bay to lay up the propellers. Our current designs are a sandwich of foam core with resin-infused carbon fiber on the outside. Once the resin sets, we can crack the mold, post-process, and now we have a brand new custom propeller. The final stage of all propulsion projects is testing. To facilitate our ability to characterize the custom hardware, we have our thrust test stand. The stand is designed to log thrust, torque, RPM, current, and voltage. Not only is this data indispensable to our design cycle, but it allows us to know how our hardware will perform before we put it on the aircraft and take flight. This gives us and our pilots confidence in both the capability and safety of our aircraft.
If you consider aerostructures to be the bones and the skin of the aircraft, then you would consider avionics the internal organs. Our avionics systems could never function without an airworthy frame, and it would never fly without someone telling it where to go. In that sense, the power distribution board is the heart, pumping the right amounts of power to each auxiliary system. Stack is the nervous system connecting all the components to the brain of our plane, and mission management is the brain, allowing us to monitor and control our missions. Now we would like to hear from our projects in greater detail.
The Power Distribution Board, or PDB, is a multi-board system designed to manage and distribute power efficiently on an aircraft. Each PDB comprises two main elements, baseboards and a daughter board. This modular system allows us to easily swap out the boards when needed. The baseboards take the propulsion batteries as input, supplying power to the motors and propulsion systems, whereas the daughter board takes in the avionics battery and supplies power to peripheral systems, such as servos and avionics communications.
This year, a brand new PDB was designed specifically for the NFC competition. The design process began with an investigation into the power requirements for the NFC motors and peripherals, as well as a revision of last year's PDB, the Albatross PDB. We've developed new and improved versions of circuits such as e-stop, current monitoring and temperature sensing, as well as a newly revised and more reliable interboard connection system. Currently, the team is in the final testing phase of our second iteration, and we plan to use these findings from this testing to complete a third and final iteration, ensuring greater reliability and performance for the competition.
Stack works on connecting the electrical components on our aircrafts and the communication both amongst them and back down to us at the ground station. We focus on the avionics in our competition drones, and our latest work on the Peregrine has been built on the knowledge learnt from our previous iterations and improved upon what has been done in the past. Using RF Design's compact receivers and transmitters, we were able to set up real-time data transmission to our ground station in flight, with built-in and external sensors collecting information. The bulk of our work consists of connecting all of these components together physically, accounting for spatial restraints and interference. Using our experience with the Albatross, we are working with Star Metal to optimize our harness with tighter wiring, sheathing, and stronger connectors, ensuring a higher standard of wiring.
As the software platform that brings together and controls all of the avionics, mission management is constantly evolving. Our preparation for NFC has brought us back to the drawing board with a redesign of the graphic user interface. For NFC, the drone will have to undertake a series of complex maneuvers. Once implemented, the new GUI will gather all critical drone data into one easy-to-read display, so that the pilots can track the drone's state as it attempts these maneuvers. New components on the GUI will show the drone's airspeed, altitude, and the G-forces acting on the plane.
In addition, the team is currently developing code that allows these maneuvers to be performed via autopilot instead of manually, which reduces the risk of human error. Instead of manually pulling off a tricky turn or loop, the pilot can simply set the autopilot to handle it. Automating the drone's flight will result in a more consistent performance and allow pilots to easily make changes to maximize our competition score. These new features are now being tested on the Mark 1 Peregrine, our current prototype fixed-wing aircraft, and every flight brings us to a closer, smarter, more autonomous system.
Hi, I'm Nick, one of the flight operations leads for 2025. Having been through our initial design process, it was now time to validate. Many lessons were learnt from the development of our previous drone, the Albatross. Drones are difficult to develop, and there's lots of risks of crashing within the first few flights. The team decided to address these difficulties by developing a 2/3 3D printed scale version of the final aircraft. The aims were to validate this design and make necessary changes to the controls so that when the full-scale version is tested, time is spent improving the design rather than fixing menial problems. We like to call this drone the Peregrine Mark 1.
One of the biggest challenges in developing an aircraft is that simulations alone cannot fully capture complex aerodynamic effects and aircraft stability. While computational models provide valuable insights, real-world testing is essential to validating a design. To address this, our team has developed a 2/3 scale, 3D printed remote control aircraft for refining our final design, dubbed Peregrine Mark 1. A key advantage of Mark 1 is rapid prototyping. Our digital model allows us to make adjustments on the fly. Once adjustments are made, the affected subassemblies can be reprinted, replaced, and ready to test within days. The aircraft is designed for ease of maintenance and repair. Mark 1 features a modular assembly, allowing most components to be detached and replaced without the need for adhesives. Moreover, the 3D printed structure absorbs the impact forces in the event of a crash, protecting key components like the battery, motors, and flight control systems. In the event of a total loss of airframe, a new aircraft can be printed, assembled, and ready to fly in under a week, minimizing downtime. By combining lightweight additive manufacturing with real-world testing, Peregrine Mark 1 bridges the gaps between simulation and practical validation, enhancing testing efficiency, reducing costs, and accelerating the development of our final aircraft.
The Mark 1 airframe represents a significant step forward in MUAS's aircraft management, motivating our flight operations team to develop new assembly and logistical techniques for managing a completely 3D printed craft on this scale. From organising new transport options to refining and formalising our construction processes, we've learned to adapt and grow alongside this airframe. For us, the craft represents an opportunity to push our tests to the limits, knowing that repairs can be done in the field with replacement parts. Mark 1 has also given us a chance to analyse fixed-wing flight in more depth than ever before, observing the performance of our fly-by-wire system by studying our flight data and building digital recreations of the exact flight.
Thanks to Mark 1's ability to rapidly iterate and evolve, we were able to implement a three-stage process to the design, where we started off with the catapult launch glider before adding a propulsion system, which allowed us to maintain steady level flight, while finally moving to its final form, which includes a tricycle landing gear system. This process allowed for our flight operations section to refine and improve their processes as we stepped through the phases of airframe. One such example being the implementation of maintenance releases, which allowed us to keep track of all aircraft abnormalities that could affect testing. Mark 1 also allowed us to experiment in many parts of the aircraft's final design, such as the control surface sizing, wing position, and many more parameters. Overall, Mark 1 represents a big leap forward for the team in terms of its flight operations and real-world testing procedures.
Hello, I'm Ruben, and this is James, and we are the Aerostructures section leads. During the testing of Mark 1, we were hard at work preparing for the creation of a full-scale aircraft. Our goal was to create an airframe that could hold up to the rigours of competition while being lightweight and easy to work on. With that in mind, we used a combination of destructive testing, simulations, and prototyping as we sought to improve our manufacturing processes and techniques.
Once our aerodynamic design was validated by the Peregrine Mark 1, we began to implement what we had learned, both in terms of aerodynamics and our composites research. We completely overhauled our manufacturing processes to produce a more optimized airframe. For example, our new wings are longer, stronger, and lighter than ever before. Now, a few of our awesome team members will highlight some of the new processes and advancements that we made during the development of the Peregrine Mark II.
In preparation for manufacturing our competition aircraft, we conducted a series of destructive tests on various composite combinations to validate and meet the design criteria for the Peregrine. This process not only allowed us to justify our material choices for the spars, wings, fins, fuselage, crux, and control surfaces, but also enabled further research and development to new manufacturing techniques. By refining our methods, we ensured a more orderly and precise fabrication process, ultimately leading us to a better final product, which is a stronger, lighter, and more efficient aircraft. As a result, we manufactured a predominantly composite aircraft, achieving exceptional strength to weight ratio with the support of Ironbark Composites. The past year has delivered some of the team's best manufacturing results to date, evident in our beautifully finished wings, skins, lightweight yet durable spars, and incredibly strong fuselage.
Also integral to maximising the strength to weight of our wings was the design of the spars. Starting with many learnings from the Albatross's design and a desire to innovate, we set down a path of testing different cross-sectional shapes. To do this, samples were manufactured and destructively tested. This began an iterative process, which in the end yielded a pair of C-section spars, a shape we haven't used before. There has been incredible progress in the manufacturing of the wings on the Peregrine. Despite being larger, they weigh barely more than half of the Albatross's wings, our previous composite aircraft. The use of well-engineered jigs provided control when bonding the wing skins onto their internal structure, minimising the amount of adhesive required for optimal load transfer.
In optimizing the physical control systems for this new aircraft, we encountered challenges at every step. The first roadblock was embedding aileron hinges into the composite wing skin. Our initial attempts using Kevlar disappointingly failed fatigue testing, but switching to nylon fabric with its high flexibility and abrasion resistance saved the live hinge concept, thus allowing us to eliminate gaps and improve high-speed efficiency while reducing weight by over 50% compared to ailerons we've made in the past. The other major issue we came across was discovered in the Mark 1 aircraft and its struggle to take off.
The original tail had insufficient pitch authority and was prone to failure due to the concentrated stress where the control surface cut into it. With a need for more control surface area and little tail left to cut into, we pivoted to an all-moving tail surface. While inspired by past design, this solution is innovative in its ease of disassembly while having all the added complexity that comes with the V-tail configuration. With this design, we aim to achieve greater degrees of control while improving overall aerodynamics, all while making it more durable.
After much work, we designed and tested a highly optimized landing gear, which is a great mix of traditional and innovative technologies. Initially iterated through existing solutions, our first take on this project was to make a rear landing gear with a 3D printed TPU spring. Unfortunately, decisions to minimize the weight of our wings made this solution infeasible. Onwards, we started developing a version 2, a carbon fiber leaf spring design. Unfortunately again, after destructive testing, we were told no by our data, as the CF test pieces and some numerical simulations indicated our mass would have to be too great to achieve a successful design. And so further, we thought up a version 3. It was the best of both worlds, a 3D printed TPU block with a levering landing strut. This design allows for our aircraft to be decelerated by the elastic properties of the TPU, with the block placed near the hinge of the lever. Its main benefits are its low weight and consistent functionality. Finally, after so many designs, we found one which worked. For the nose gear, which takes significantly less force on landing, we come up with a simple caster wheel design that has worked well and allows for smooth taxiing of the aircraft.
I'm going to turn this around before I break it. All right, Tom, I reckon we've built enough suspense. What do you reckon?
I think I agree. So without further ado, please see the Peregrine Mark II on the screen.
Well, there it is, Peregrine Mark II. Tom, what can this drone do?
So this drone can fly at speeds of up to 160 kilometers an hour, carry 17 liters of payload, and it's so efficient that if you cut the motors when flying at an altitude of just 100 meters, it will glide for almost 2 kilometers before touching down. But there's more, and if you want to find out exactly what, come find me or any one of the Aerostructures technical members after the presentation, and we'll take you through some more of the specs.
We'd take questions, but I think we'd be here for a while, so. This is the result of years of hard work. I say years because I think it's generations of the team that have kind of helped come up with such an incredible platform.
and our current team's tireless efforts. This drone is here ready for the global stage. Tonight, we have spent time focusing on our incredible team and what they have accomplished in the last year. However, it is our incredible supporters that provide us with the resources and expertise to be able to pull this off. Without them, none of this would be possible. From Leap Australia, who provide our team with 3D design tools which bring our visions to life, to Altium, who ensure our avionics team have access to the latest virtual tools in electronics design. Style Metal, who provide our team with expertise and advice on elegant wiring solutions. And of course, Monash University, our faculty. They provide us with facilities and the organisational oversight to be able to excel. These are a few among many of our supporters. I would also like to extend a special thank you to Adam McMahon. Unfortunately, he couldn't be here tonight, but it was his property which we did most of our testing in 2024. This last year, Adam has hosted us more times than I can count. His generosity to the team is second to none. To be able to support this team, I think, is an incredible opportunity. We harbour some of the greatest young minds in engineering, students who are in the fast lane to becoming subject matter experts. To support this team means to have direct access to that pool of talent, to have access to media and marketing opportunities, to have your organisation associated with Australia's #1 university for engineering. To support this team means to, as an organisation, contribute to a great cause, young minds trying to make a difference. So spread the word that MUAS is here and is a cause worth supporting. Tonight, we also open our recruitment. We're taking members for all sections from all degrees. This is the year UAS returns to the global stage. So if you want to be involved, we'll need all the help we can get. If you're someone with an interest in electronics, aircrafts, or just organising things, we'd love to have you on board. Our team offers a special experience for people from any background, an experience that's hard to find anywhere else. I'd like to close tonight by thanking everyone for joining us in celebrating the achievements of this team. We truly appreciate the support of everyone who has been part of the journey. In addition to our supporters, we would like to extend our thanks to friends and family. We are so grateful for your unwavering support, even when we're a bit hard to reach, being so invested in our work. To my team, standing up there, you are an extraordinary group of individuals. And this aircraft, this night, stands as proof of what can be achieved when passionate people dedicate themselves to a shared vision. It truly is my privilege to lead such an inspiring group, and I can't wait to see where you take us this year. To everyone, stay tuned. Be sure to follow us on our socials and be part of this next incredible phase of our journey. That's all from me. On behalf of our fantastic team, thank you.
So that concludes the presentation portion of tonight. We'd like to welcome you to the top of the stairs where we have organised some refreshments and an exhibition of all our team's work. They are so excited to showcase their work. So, have a great evening and enjoy.